Now let's discuss Big Omega notation. Big Omega notation is analogous to greater than or equal to for functions. Big Omega of g of n is the set of all functions f of n such that there exist positive constants c and n naught, such that for any n greater than or equal to n naught, f of n is bounded below by c times g of n. Notice that we are still dealing with non-negative functions. In the graph, we have the same functions, but in this case, g of n is log of n, and f of n is n squared. We can also apply the limit rule. F of n is in big omega of g of n, if and only if the limit of n goes to infinity of f of n divided by g of n is greater than 0. That means it can be constant, or it can be infinity. I wanted to mention that the textbook also mentions little omega and little o, and both of those you can think of as strict inequalities. So the limit cannot be a constant in either case. Let's now discuss big beta notation. Big beta of g of n is a set of all functions f of n such that there exists positive constants c1, c2, and n naught such that for any n greater than or equal to n naught, f of n is between c1 times g of n and c2 times g of n. This is analogous to the equal sign for functions. So in this figure now, we have that f of n is 2 log n, c times g of n is 4 times log n, and c1 g of n is 1/2 log n. We can also apply the limit rule. So a function f of n is in theta of big theta of g of n if and only if for some positive constant k, the limit as n goes to infinity of f of n divided by g of n is equal to a constant. So this is why we are so careful with big omega and big O, is because if a function is in big theta of g of n, that means it's in big omega and big O of g of n. Let's try a practice problem. And for this practice problem, we want to remember the changes of basis formula. So that is log in base b of n is equal to log of n in base a divided by the log of b in base a. So you can think of this as the change of basis constant. And this is some of why computer scientists are a little bit sloppy in mentioning the base of the log when we take asymptotic notation, because it only differs by a constant. But I do want to mention right now that usually if computer scientists leave off the base of a log, we often mean log base 2, whereas log without a base in most math classes is log base 10. However, we are careful with the natural log, and we usually mention ln for that. So we would like to show that log base 10 of n is in log base 2 of n, is in big theta of log base 2 of n. And to do this, we need only apply the limit rule. So here we have the log base 10 of n divided by the log base 2 of n. And in order to evaluate this, we want to change from log base 10 to log base 2. And when we do this, we will get the log base 2 of n divided by the log of 10 base 2 divided by the log of 2 base n. And when we do this, we are just left with a constant, which is the log of 10 base 2. And our limit is a constant, so we can say that log base 10 of n is in big theta of the log base 2 of n. And this is why we're not so careful when we're talking about asymptotic notation to specify the log.